is how we deal with gases. And we decided in this unit, we're going to just do gases in under one condition that's called standard temperature and pressure. And then in a future unit, we'll do a whole separate unit just on gases and gas laws, like later on next month. And then the other issue is whenever you have solutions, like you've got solutions of ionic compounds, or it could be like a acid or a base, and we'll deal with that when we do acids and bases. So for now, I got to tell you about how things work for measuring molar quantities with gases, and there's a standard unit called molar volume. But this is a diagram that's from your textbook that relates relative quantities of different kinds of things. And all the time, the quantity, the mole, is the like the clearinghouse or the gatekeeper through which you relate quantities. And like you can measure a mass of substance, convert from mass to a number of moles. You can talk about like numbers of particles, individual particles, and it takes 6.02 times 10 to the 23rd of them to get to a mole. But then there's this issue of volumes of gases to get back and forth to moles. All right, so there's like a guided notes thing here, and then there's like a worksheet with some different stuff on it and whatnot. So the idea of volume is just how much space something takes up. It's just how much room. The bigger the thing, the greater the volume. Gases can take up any kind of different volume. So maybe you have a flask or a beaker full of a gas, or maybe it's a gas in an envelope, like in a hot air balloon or something like that. However much space it takes up, the air in this room takes up space. So this room has a certain volume. There's a certain amount of gas in this room. There's a certain amount of oxygen in this room that could burn. You could take the oxygen in this room and use it to burn wood or paper or something like that. There's a limit to how much oxygen is present. How much volume something takes up depends upon how packed things are. So, one of the fundamental differences between solids, liquids, and gases is when you have the solid phase, individual atoms are usually oftentimes in a regular repeating arrangement, so that the atoms are like up against each other, and they aren't necessarily, rectangular in organization or whatever like that. But for many ionic compounds, they form individual crystals, and there's a regular packing. For liquids, liquids have approximately the same density as solids as compared to gas, but in liquids, like the particles are more like randomly arranged. They can move around relative to each other. So the fundamental difference between solids and liquids is that in liquids, the particles are free to move around. They take the shape of the container, but solids, they're usually fixed or rigged in size. But for gases, if I'm going to draw this volume and show like this many particles of solids, or this container and have some liquid in it where they're all around, if I have the same volume for a gas, I might draw one, because it turns out that gases are only about 1,000th the density of liquids. All right, so here's like an example. That's 1 mole of water. It's 18 milliliters of water. That's 1 mole. This quantity of water in this graduated cylinder, that's approximately 6.02 times 10 to the 23rd molecules. That's it, 1 mole of water. But 1 mole of air, this is like our standard molar volume box. 1 mole of air is 22.4 liters, about that volume. So if I were to have to take, this much water and pour it into a box this size, I need about 1,000 of those volumes to fill this up. So what that also means is that the distance between atoms or molecules in samples of gases is about 1,000 times difference in distance. If like at the bottom of the thing here, I'll draw like a line. So if this red line maybe represents the distance between two like maybe oxygen molecules in the air in this room, so that there's some distance apart. This distance would be a factor of 1,000. The distance between water molecules, on the other hand, would be only 1,000th of that, or the distance from here to here is just, let me draw it this way, distance from here to here is just 1. So the distances between atoms or molecules for gases is significantly further spread out. That's one thing that makes measuring gases difficult, is that uh, because the density is low, and also that the gas is compressible, you can change the volume of a gas easily. Uh, the space between the molecules depends upon temperature and it depends upon pressure. So if you increase the temperature of a gas, the volume is going to be bigger. And if you increase the pressure of a gas, the volume is going to be smaller. It's not like that with liquids and solids. Like if you put water in a graduated cylinder, it's slightly dependent upon temperature. In other words, when you heat up water, it expands a little bit. When you cool it down, it contracts a little bit, but not by much. So we don't really worry about differences in volume with temperature for liquids. For solids, you just throw them on the balance and weigh them. If you heat up a solid, it might expand, but it's not going to weigh any different, uh, like appreciably or significantly in the lab. So the issue is that the volume of a gas depends upon temperature and pressure. So all we're going to deal with is one type of condition. Uh, Whenever you measure either mass or volume, we use two different terms. The mass of a mole of substance is called its molar mass, but the volume of a mole of substance is called its molar volume. These are pages in it's like on the second page. So what molar mass means is if you have a solid, maybe I have like a chunk of coal. So here's like a chunk of coal. There's some coal. And coal is made of carbon. The formula mass for carbon is that it's 12 grams per mole. It's like 12.01 grams per mole, meaning if I want 1 mole of carbon, I just need 12 grams of it. But molar volume is more useful for gases. So when you have a gas, maybe something like, oxygen, oxygen is O2, and its formula mass is about 32 grams per mole, but you can't weigh out oxygen. Instead, you have to meter its volume out volumetrically. You've got to like have a way to measure individual volumes. In the aquarium that's in the main office, but also in the fish room, I take carbon dioxide and meter out carbon dioxide, but I have to do it by volume. So there's this, it's it's a pain and it's expensive. I'll show you. It's this thing called the carbon counter. Let's see. Got to change the screen here in a second. Let's see. New share. This thing. So what this little thing does is you hook this up to a tank of carbon dioxide, and it has a couple different pressure reading valves, and this is a pressure regulation valve, and this little thing here meters out quantities. And inside there's a little trap, and a valve opens up, CO2 comes in, the door closes, and then the next door opens up, and CO2 goes out. So it's like a little kind of like trap door thing where gases get to escape. And that way, every bubble has the same volume. And then this thing here says seconds per bubble. You can adjust like how many seconds there are between individual bubbles. And that allows me to like dose carbon dioxide into the planted tank in the main office, because plants like the water to be a little acidic and have some extra carbon dioxide. And we use them in the fish room to break down limestone to make calcium and carbonate ions so that more coral can grow. Those are like $389. I got 4 of them running right now. It's a lot of money. That's just for dosing out volumes of gas. It's a very difficult pain in the butt. Then there's also pH controllers, which determine like the that measure the pH, because it turns out as you change, this is the one I use, as you change the amount of carbon dioxide in solution, it changes the pH. So this device then in real time measures the pH of the water, and it determines to turn the thing on and off. So That's the way we do that. That's kind of an exciting kind of deal. The old school way is to use this, and then you have to like constantly every day like adjust this little knob and count the bubbles. Like sit there with a stopwatch and count the bubbles and measure the volumes of the bubbles out. All right, so that's that deal. I'll tell you what that standard molar volume is then. Uh, so here's the thing about Avogadro's number. It turns out that the origin of Avogadro's number is 6.02 times 10 to the 23rd, 6.02 times 10 to the 23rd. That's called Avogadro's number. But Amadeo Avogadro's hypothesis and the origin of Avogadro's number is based upon gases. And it turns out that by studying chemical reactions involving gases, Avogadro noticed that as long as the gases had the same temperature and pressure conditions, that the ratio of the volume of gases is the same as the molar ratio in the chemical equation, which means that every time you've got two different gases, as long as they're at the same temperature and pressure, they have the same number of particles. And that's a really, really, really nice thing. So what I mean by that is, let's say you have a box and it's got some oxygen in it. And maybe that box has 3 moles of oxygen. And this thing about temperature and pressure, if they're at the same temperature and the same pressure. So let's say it's just, room temperature. Uh, room temperature is about 20 degrees Celsius, and atmospheric pressure can change. And there's one unit of pressure called the atmosphere, 1 atmosphere pressure. So if you have that box and it's got oxygen in it, there's 3 moles of oxygen. If you were to happen to have the same box, the same size box, but with a different gas, maybe carbon dioxide, you would also find that it is also exactly 3 moles. So no matter what the species of gas is, it could be a very lightweight gas like hydrogen with a formula mass of 2, all the way up to uranium hexafluoride has an incredibly high mass. Let's see, 6 fluorines is like 100. Uranium hexafluoride has a formula mass of around 400. So hydrogen is only a mass of 2. Uranium hexafluoride has a mass of 400 grams per mole. But those two gases at the same temperature and pressure condition would have exactly the same quantity of particles. They would have a different weight, but they have the exact same quantity of particles. So I'll tell you, that makes things easy for us because the world could be a lot more difficult for measurement for gases, but that's a fact. Okay, so here's the thing you got to know. We have standardized different types of temperature and pressure conditions to adjust all of our calculations to, and you need to know about this and kind of commit it to memory. Standard temperature and pressure, we abbreviate that as STP. So anytime you see the abbreviation STP, STP stands for standard temperature and pressure. That's what the STP is. And the standard temperature and pressure condition is 0 degrees Celsius. 0 degrees Celsius is the freezing point of water. That is 32 degrees Fahrenheit. But the freezing point of water is a good standard to work by. And then standard atmospheric pressure, there's a unit of gas pressure called the atmosphere. ATM stands for atmosphere. So you might know that atmospheric pressure varies or changes from day to day. It's important in meteorology. We know that whenever it's terrible weather outside, it's raining, there's a thunderstorm, it's just gross. Atmospheric pressure is low during those conditions. And anytime it's like a nice, bright, clear day, atmospheric pressure is higher. So one indication we use to determine is weather getting worse or getting better is to look to see is the atmospheric pressure changing. If atmospheric pressure is dropping, that means the weather's getting worse, generally. If the atmospheric pressure is going up, that means the weather's getting better, generally. The lowest atmospheric pressures ever recorded are in the middle of hurricanes. And then high atmospheric pressures exist near sea level on completely clear, bright, sunny days, especially when it's the wintertime. So if it's like super cold, on days when it's like super, super cold, but the sky is super clear and it's really bright. Uh, like yesterday afternoon was like that. Atmospheric pressure would have been very high. So that changes the volume of gas, because what happens is if you have a volume of gas like this, and if the atmospheric pressure increases so that you get pressure pushing on the gas, that volume or parcel of gas will shrink. It'll become smaller in size. So standard temperature and pressure is, for us with a metric unit, 0 degrees Celsius and 1 atmosphere. These other values are in other units that we use commonly in chemistry. This unit, the millimeter of mercury, is a unit related to how much pressure, or when 1 atmosphere of pressure can support a column of mercury that's 760 millimeters high. If you watch the weather at night, or look on your phone and look and see what the weather is, one of the common indicators is to tell you atmospheric pressure, and it's usually in the unit of inches of mercury, or people will just say inches. And standard atmospheric pressure, when people talk about it colloquially in meteorology in the United States, it's around 30 inches of mercury. This unit over here, kPa, is the kilopascal. And you don't have to know anything about those for now, but those are common units. This is based upon the standard units. The kilopascal, a pascal is the same as a Newton per square meter, which is a standard unit of pressure based upon this definition of force per unit area. So all we're going to deal with for now is just gases at standard temperature and pressure, but we will do problems where we have to adjust volumes to STP in order to use Avogadro's number. So here's an example. This is the number you need to know, 22.4 liters. So this box, it's got a bunch of things on it. See, it says 0 degrees C or 760 millimeters of mercury. That's 1 atmosphere of pressure. This box contains 1 mole, which is 6.02 times 10 to the 23rd molecules. We call it 1 gram molecular volume, but its volume, this is 22.4 liters. So the air that's in this box, we're pretty close to STP conditions. There's about 1 mole of gas in this box. Just the same as there's 1 mole of water in that container. The formula, or the molecular weight of water, is 18 grams per mole, and water's density is 1 gram per milliliter. So 18 milliliters of water is a mole, but for air at STP, 22.4 liters is the standard volume. And it turns out that that's not an approximation. We have standardized things in the metric system with the molar quantity to be fixed to this quantity. So here's what that means. If you have 3 containers, helium, oxygen, and carbon dioxide, and they all have the same volume, so the volume is 22.4 liters, they're all the same size, just like that box. They all contain the same number of moles. This is N. They're called the N number, the number of moles. But because helium, oxygen, and carbon dioxide have different formula masses, they all will weigh a different amount. It's not practical to weigh gases. Like, especially like if you put helium in a balloon, not only does it make the balloon weigh more, it's buoyant in the atmosphere, so it pulls up. If you put nitrogen or oxygen in a container, that's neutrally buoyant. It won't like weigh anything. It's like if this box had nitrogen in it and I put it on a scale, it'll tell me how much the box weighs. If I take all the nitrogen out so it's vacuum inside, it'll still say exactly the same amount. So you can't weigh out gases. You can only figure out quantities of gas based upon their volume. So that's why we have to use this standard molar volume. So you can write that as a conversion factor. 1 mole is the same as 22.4 liters, or you can write 22.4 liters is 1 mole. That's if it's a gas. So that volume of liters can be used to measure volumes of liquids. Like you can have a 2-liter bottle of soda, liters of volume of liquid, but liter can also be the same as the unit of volume for gases. All right, so any gas has a molar volume of 22.4 liters, and that is at STP. These are the two different ways you can write the conversion factor. You can either write 1 mole over 22.4 liters or 22.4 liters over 1 mole. So if you're converting from moles to or from liters to moles, you use the first conversion factor. Or if you're converting from moles to liters, you use the second conversion factor. So that's the basic. That's what you got to know. So this is an example. You got 1.3 moles of NO2, nitrogen dioxide. What kind of volume does that take up? So 1.3 moles, and using the conversion factor to get you from moles to liters, every 1 mole of a gas has a volume of 22.4 liters. So just the same as we can convert from like moles to grams for solids, you can convert from moles to liters as a volume for gases. And the math here is just 1.3 times 22.4. This only has two significant figures. I mean, my calculator says 29.12, but it'd be 29 liters. So if you want to have 1.3 moles of a quantity of NO2, you, at 0 Celsius and 1 atmosphere pressure, have a container that has a volume of 29 liters, and you'll have 1.3 moles. So that's how you convert from moles to liters. If you want to go from liters to moles, 40 liters to convert to moles, every 1 mole has a volume of 22.4 liters. So with every conversion factor we've ever used, whatever unit you begin with is the unit that's in the denominator of the conversion factor. And then now it's 40 divided by 22.4. So my calculator's got a whole bunch of digits, 1.785714286. You don't want all that stuff. This 40 liters has 3 significant figures. So 1.79 moles is good. Like, we could measure the volume of this room and figure out how many moles of gas are in it. That's not a difficult thing to approximate. So we've talked about natural gas a bunch of different times. Natural gas is mostly methane. So here's the thing about natural gas. Methane, when it comes out of the ground, natural gas, it is odorless. It does not have an odor at all. So in a way, natural gas is somewhat dangerous that it doesn't have an odor, because if you were to have a natural gas leak in your home, you would not know it. But natural gas, when you, like, if you open up the lab valves to let natural gas out, it does have an odor, and that's because an odorant is added to it. We add a chemical to the natural gas so that you can detect it, so you can smell it. And that way, if there is a leak, even like if you have a gas range and you turn it on, like as you're lighting it or it's initially running, it has that little bit of an odor. That's the odorant added to the natural gas. If that odorant weren't added, you would never smell anything. So it tells you not only that something is kind of running, but also if the flame is not lit and you just have raw gas going out, you can detect it very easily. Also, like if there's a natural gas line that breaks underground in the city, that odorant will seep up through the ground with the gas, and you can walk down a sidewalk and maybe smell it and then report it. Because otherwise, if it's not if it's not windy, that natural gas could seep up through the ground and collect, and a car could drive by and you'd have an explosion. That'd be dangerous. Also, a little hint: sometimes there could be a furnace or hot water heater or something where the pilot light goes off, or natural gas leaks into your home. If you ever, and the house is like empty, nobody's in it. If you go home and you open the door and you smell that, don't go in, don't turn on a light switch, because the proportion of gas could be just right, and you could like blow the house up. I don't know if you've ever seen, it happens from time to time, natural gas house explosion. Just find a picture. It's usually pretty cool. Like, I mean, it's not cool, but it'll take the whole house out. Let me get to new share. You can look at these like all day long. This is like what it does. So, oops. Like there was a house there. That was that was the house. And then those are all the bits and pieces of the house, you know? It goes all over the neighborhood. So don't be like, boy, it smells bad in here. I'm gonna hit the light switch and see what happens. And unfortunately, sometimes people die, you know, but it's also can be true that like the gas could start leaking and no one's home, and then something ignites it, something electrical with a spark, and then they're forever. Here, look at all the. That's a pretty good one. It looks like confetti. Like then all your stuff is everywhere, all over the neighborhood. This is probably the. Is that the same one? That's a nice one. Not to scare you, but you know, it happens. It's very rare. So the reason why that problem says natural gas is mostly methane, we actually use the terminology natural gas and methane separately. Methane itself, CH4, is colorless and odorless. But once we add the odorant to it, then it's sold and called natural gas. So like here in Pennsylvania, we do a lot of hydraulic fracturing, and that when the wells are fracked and the gas comes up and it's compressed and sent through the pipelines, that's odorless. You can't smell it. And then at the compressor stations is where the odorant is added. So now in all these problems, it doesn't matter what the chemical is. It doesn't matter that it's methane. It didn't matter that it's oxygen. It doesn't matter at all what the substance is. Every substance, every gas at standard temperature and pressure has the same volume. So you know, if you convert from uh, liters, you can convert to moles first. You always have to convert to moles. So 8.9 divided by 22.4, 8.9 liters of gas is 0.39732 whatever mole. Once you convert to moles, then you can convert to a mass. And now the mass of the substance matters. So CH4, methane, I got 1 carbon and 4 hydrogens. Carbon's mass is 12.01. Hydrogen is 1.01. So that's 16.05. Once you know the number of moles, then you can convert from moles to grams. I left some extra significant figures because that's an intermediate step, but every mole has a mass of 16.05 grams. So now, let's see, 16.05, or if you leave it in your calculator, then you can just multiply the answer by whatever, 6.3, I guess we have two significant figures, so 6.4 grams. But there's another way to do it, and that's that you can put conversion factors right beside each other. So a more efficient and smarter way to do the problem is if you just write 8.9 liters, you can first just convert to moles. 22.4 liters is the volume of 1 mole. And you've eliminated this unit liter, and then you can convert directly into grams. 1 mole has a mass of 16.05 grams. And then the unit mole cancels out. But you can't convert directly from liters to grams. You can always convert to moles. You should always convert to moles. So if you start with a volume that's for a gas at STP, you can use Avogadro's number to get from liters to moles. That's the 22.4 liters. And then once you can convert to moles, then you can convert to the mass in grams. I mean, it should be exactly the same thing. Like I did the same thing. I kept the answer. So yeah, 6.4 grams. So it doesn't matter if you want to like convert it into moles first and write that down and then convert to grams, or do the problem in 2 steps. It's or do two conversion factors side by side, because then it's really like 1 step. Convert from liters to moles, and then from moles to grams. So this 16.05, that's the formula mass. We didn't use that in the previous two problems, because here with the moles of oxygen, you convert from liters to moles, the mass doesn't matter. Here that it's NO2, from moles to liters, the mass doesn't matter. The only time mass would matter is if you start with a mass or you're trying to find a mass. So in general, all the time, the quantity, the mole, which isn't actually like the little animal, but we use it like as a mascot or whatever, you can convert from volume to moles. That's for gases. You can convert from numbers of particles to moles. You can convert from mass to moles. So if you want to go from a mass to a volume, you convert from mass to moles to volume. You want to convert from volume to number of particles, you convert from volume to moles to particles. Or if you want to convert from like mass to number of particles like we already did, you convert from mass to moles and then to particles. And the conversion factors here are that 22.4 liters is the volume of a mole, or the molar mass, which is the formula mass, is the mass for 1 mole, or Avogadro's number is the like number of particles per mole. So people call the 22.4 Avogadro's constant, Avogadro's law, but this is Avogadro's number. Avogadro's number. This 22.4 liters is oftentimes called Avogadro's law. Because the law is that STP, standard temperature and pressure, every mole of a gas has a volume of 22.4 liters. So let me go back to this other problem that I mentioned yesterday to relate quantities as well. This is like one more quick example. That example of burning octane, which is a component of gasoline, like in an automobile. I got 2 there, I gotta have 16 here, I gotta have 18 here, and 25. Here's what the chemical equation tells you, is that for every one reaction, you need 2 mole of C8H18, and then you need 25 mole of oxygen. So here's what's really cool, I guess. When you like drive down the road in a car, if the car has a gasoline engine, you got to buy these 2 moles of octane. But these 25 moles of oxygen, they're free. So to make the reaction happen, you need 27 molecules. 25 of the 27 molecules, they're free. They're in the air. They're just, as you're driving down the road, you're just getting the free oxygen. You got to only buy these 2 moles of octane in the gasoline. So as a fuel, it's a kind of a pretty good deal like that. If you relate the volumes, this octane has a fairly small volume. Like for every about 1 liter of octane, because not only are there 12 times more molecules of oxygen, but gases take up about 1,000 times the volume. You need about 12,000 liters of oxygen. So the ratio of molar quantities is about 12 to 1. But then oxygen has a volume that's about 1,000 times bigger because it's a gas instead of a liquid. So as a ratio of molar quantities, for every 2 moles of octane you buy, you get 25 free ones in the air. But because this is a liquid and this is a gas, for every liter of gasoline you buy, which is about 1/4 of a gallon, the engine has to take in about 12,000 liters of air. So volumetrically, the air, the oxygen that you're consuming as you drive down the road is significantly greater than the volume of the liquid. So if you buy 10 gallons of gas at a gas pump to like fill up your car, that requires about 120,000 gallons of oxygen gas as you drive down the road. So if you pump 10 gallons of gas into your car, once you've driven that 10 gallons of gas down the road, you've used on the order of about 120,000 gallons of oxygen from the air, which is quite a lot of oxygen, you know? So not only do you consume a lot of oxygen, but you also create a lot of carbon dioxide, enormous amount of carbon dioxide. And, water vapor too, but you make a lot of carbon dioxide. So it isn't like you buy 10 gallons of gas and you make like 10 gallons of volume of CO2. You make enormous quantities of carbon dioxide. In that proportion, about 60,000 gallons of carbon dioxide for every 10 gallons of gas you consume. 60,000 gallons is like about 3,000 of these boxes worth of carbon dioxide for every 10 gallons of gas that you burn. And this has a volume of about 5 gallons. So a lot of CO2. All right, there are some problems here for you to try. It doesn't say anything at the top, but it's the single paper. For all gases at STP, 1 mole is 22.4 liters. So there's just something to practice here. Convert from moles to the volume in liters. Number 3 is converting from liters into number of moles. And then some other ones, 4, 5, 6, and 7. You've got to convert always into moles, but then you might have to figure out number of molecules or a mass in grams, some kind of quantity like that. Ooh. Looks like in about, depending upon the manufacturer, between 5 and 15 years from now, there won't be any gasoline-powered vehicles. Ford's made the commitment by 2035. Volkswagen, which is the largest manufacturer of vehicles in the world, they will not design any more gasoline-powered vehicles and plan to stop selling their last gasoline-powered vehicle in 2025. So, uh, it, anytime I see a gas station like being refurbished or remodeled, seems kind of weird because, I mean, gasoline-powered vehicles will still be around, but once the last one's sold, then there'll be fewer and fewer of them. And that'll be it. It's very likely that it's very difficult to exactly predict the future, but it seems like somewhere between 20 and 30 years from now, we just won't have, might not be allowed to use gasoline powered vehicles. Just go electric, drive around like that.